Okay, what we're going to be doing today is going to be looking at some circles and some different segments in circles. This thing, of course, the green thing on our screen is a circle. And a circle, if you want a formal definition for it, we're going to be taking some notes on page 247. A circle is just all the points that are equidistant from a point. And that point that all the other points are equidistant from is called the center of the circle. So this point I'm marking in purple would be the center of the circle. It's just the point right in the middle, pretty obvious. Just to make sure we know these things that should be reviewed hopefully for most of you. The radius would be this line in green here. That line is the radius. The radius is basically the distance from the center to the edge of the circle. So that is your radius. Radius is your distance from the center to the edge. So as we are looking at these, the circle is all those points around that center that are equidistant, and the distance they are from is the radius. Now, other things about a circle that you may have seen before, maybe not, is a chord. A chord is basically like what I have here in orange that goes from one point in the circle across to another point in the circle. So that is a chord. It goes from one point to another point of a circle. So a chord, you can basically call it a segment that connects 2 points on the circle. And then another thing that comes up is a diameter. Now, a diameter is basically a chord that goes through the center. So you might have thought about the diameter before as being twice as long as the radius, and that's a good way to think of it, because if I move this chord up here so that it goes right through the center, you can basically see my diameter is still a chord. It goes from one side of the circle to the other, but it is correct that I have a radius on this side and a radius on that side, and if I put them together, I create this chord, this diameter that goes all the way across the circle. So you can think of the diameter either as a chord that goes all the way across the circle, or you can think of it as two radiuses. Either way is correct. And a very important thing for the diameter is that the diameter is equal to 2 times the radius. Because sometimes they'll give you a diameter, you'll need a radius. Sometimes they'll give you a radius and ask for a diameter. So you just need to remember diameter is twice as long as the radius. Also, we have these other lines called secants and tangents. Secant is this blue line I've drawn here, and it's basically a line that goes through a circle. So it's going to intersect the circle twice. It's going to go through a circle, and it is correct to say that the secant contains a chord. So that thing there would be a chord. The chord just stops on the circle, though, and the main difference between a chord and a secant is, once again, a secant is a line that goes through 2 points on a circle. My pen just decided to go small on me. I hope you can read that. But it's a line that goes through 2 points on a circle. Okay. The next thing we need to look at is tangent. And we've gotten this screen kind of full, so I've gotten another thing for tangent. And this line here is a tangent line. I'll go over it in purple maybe here. This tangent line here is a line that touches a circle once. So a secant went through 2 points on a circle, so it actually sliced into the circle. The tangent just touches the circle once, so it just barely touches it, and it's like it just skims off the edge of the circle. It doesn't actually cut into the circle, it just touches it and keeps going. So there's your tangent. And this point right here is called my point of tangency. That's the point where the circle touches that. Now, the point of tangency is very important because if I take my radius line that I had here, at the point of tangency, a radius always makes a 90-degree angle with a tangent. So one thing we're going to use about tangent lines is they always make a 90-degree angle with a radius, which means we just have a right triangle. So it's important to know that the radius is perpendicular to the tangent at that point of tangency. And that means we have not only a right angle at the point of tangency, but if we draw another segment like this one I have in blue here, we will actually have a right triangle. Now I'm going to go ahead and show you a problem we can work with that. You should have some space to work out this example on 245. One thing they might say is we'll go ahead and label some of these segment points. So let's say that this is point A, this is B, and this down here is C. They might come out and tell you something like this. Let's see if I can get a little room to write here. AB, they might say is 3. So this circle has a radius of 3. It might say BC is 4. And it could ask for the length of AC. Well, since AB is a radius, and BC is a segment on a tangent line, and B is the point of tangency, it's where they do. I know I have a right angle here at angle B, and I know that this ABC is a right triangle. So since it's a right triangle, I can use the Pythagorean Theorem, and I'll have 3 squared plus 4 squared equals C squared, where of course C is this here. So 3 squared plus 4 squared is going to be equal to 9 plus 16, 25 is C squared. So that means C is going to be 5 after I take the square root. So AC is equal to 5. So that is one way you can use these tangent lines. If you have a length of a segment on a tangent line at the point of tangency, you have a right triangle, you can use Pythagorean Theorem and find the missing piece. Of course, they could have given you AC and instead of BC and ask you to solve using the Pythagorean Theorem. Of course, we've done problems where you have to solve for a leg instead of a hypotenuse. Lots of different ways they can mix these up, but be on the lookout for right triangles anytime you have tangent lines. One other thing I want to point out, though, is sometimes they have another point here, like they might mark this as point D, and they might want to know what's the length of DC. Well, to find the length of DC, the key thing to get that is to realize that AC from here all the way down to here is 5. And also to realize that this right here is another radius of the circle. AB is a radius, AD is a radius, and every radius is equal because a circle, all points on the circle are equidistant from the center. So AB and AD have the same length. So AD has a length of 3. Which means the distance from D to C would have to be 2. Once again, the reason I know that is if I know the whole thing from A to C is 5, as I found here, if from A all the way to C is 5, and the radius part is 3, the part that is outside the circle from D to C that I'm going to mark here maybe in red, this part we were looking for here, is going to be the other 2 because 3 plus 2 is 5. So that's one thing you can use with these tangent lines. We're going to look at a couple more definitions now. Tangent circles are like these circles I have over on this side. So these circles here are tangent, and that means that they touch at a single point. Their point of tangency is right here in blue because you can see they touch there, and you could actually stick a tangent line right through the middle of those circles. Now, it turns out that these circles, sometimes you'll have a question that says, how many tangent lines can you have for this pair of circles? Well, these tangent circles, clearly you have a tangent line there, but in these, since they have roughly the same radius, you also have a tangent line that would go there. That would be tangent to both circles, and you would have a tangent line there, which would be tangent to both circles. And any tangent line that touches more than one circle is called a common tangent. So if it ever asks you, What is the common tangent, or how many common tangents? Common just means it's a tangent line that is tangent to more than one circle. So this one is actually exactly like number 7 that you're going to be doing on your homework. And it's going to be, your common tangent is, your answer is there are 3 common tangents to that pair of that pair of tangent circles. Now, on page, the one we did skip is concentric circles. These here, right here, are concentric. Concentric means they share the same center. Con means with or together. So these are circuits with the same center. Sorry, I need to spell that correctly. Concentric. Reasons I don't teach English once again. So concentric circles have the same center but different radiuses. It almost looks like ripples on a pond. Like if you've thrown a rock into a pond, it's how the ripples would spread out. That's what concentric circles basically are. And concentric circles have no common tangent lines, because a line that is tangent to any one of these circles, like if I draw this line here, that would be tangent to that circle. Clearly, it's going to be a secant line to the other larger circles, because it doesn't touch it as a single point. It slices all the way through it. So concentric circles have no common tangents. I hope this vocabulary review helps you. There is one more thing I do want to mention to you, and that is circles with common tangents. So let's look at this real quick together. Okay, so what I've done here is I've redrawn this so that I have 2 tangents to the same circle. So I have this line A to B is a tangent, and A to C is a tangent. They will either have to tell you that these are tangent lines, or sometimes they will draw in the radius, and they'll mark that they are both making a right angle to the radius so that you know they're tangent lines. Well, first of all, one thing that you can notice is that these 2 radiuses have to be equal, and I have a 4-sided figure, and that these opposite things are equal. So what I have actually created here with these tangent lines is a kite. Because I had those 2 sides equal, the opposite angles are equal. It turns out that these are equal. So I have a kite, which was one of those 4-sided figures, the quadrilaterals, that had adjacent sides. Adjacent sides that are congruent to each other. Well, the key thing to here is what I like to call this is the Party Hat Theorem, because what will happen is if I am given 2 pieces of information, like if I was told that AB was equal to 2x and AC was equal to 10, I know that the 2 tangent lines that meet in a point, anytime I have 2 tangent lines to the same circle that meet in a point, I know they have to be equal because they form 2 sides of a kite. So that means I have 2x is equal to 10. And that means I can figure out that x was equal to 5. So that's a way you can solve a simple equation and figure it out. But anytime you see 2 tangent lines on the same circle that meet in a point, you can know that the 2 sides of those things are equal. It's basically like the 2 sides of a party hat. So this side of the hat and this side of the hat are equal. And you can kind of see, like, see, it's a little man there with squiggly eyes and a funny nose and a mouth. And maybe he's, resting in his party hat, I guess. Maybe he's partied a little too much. But anyway, that will help you know how to do those problems when they come up as well. If you've got any questions, feel free to ask. Hope you have a great day.